Alright, hello. Sorry if there was indeed no audio there before. Let me just get the project set up here for the tutorial. I'll go and I'll turn off my glitchy video as well. So today we'll be doing a heap once again. This is going to be the same content as Monday's section, just revisited again for those who aren't able to make it to Mondays. We'll do similar stuff. Here I'm just going to check out the not solutions version of the branch. And I'm going to reset it as well. And I'll send the GitHub link in the chat shortly. Where is it? Oh, that's weird. Yeah, reset head. Hard, just getting rid of my nonsense here. And we've got a heap and everything's empty. Alright, awesome. And I'll approach it differently today a little bit as well in our explanation. But before I do, I'll explain a quick bit on the difference between heaps and binary trees. Why are we doing heaps? Why do heaps matter? What is a heap? Well, a binary tree, a binary search tree, is a data structure we're pretty familiar with now, I hope. If not, there are previous tutorials which cover it in a lot of detail to help you out. But essentially, a binary search tree, it's got a node with its left and right children, and its left and right children are determined by where they appear in sort order. So we've got, our middle one here, and then a smaller one on one side, larger one on the other side. Simple stuff. That's a binary search tree. Now, when we're actually going to make it into a heap, we need to follow a certain amount of rules. And why these rules are important will actually come in handy very soon. And I was planning to make a animation for it for today, but I got delayed, so it's probably going to come out a little bit later, where I explain how this exactly turns into an array. That's one of the purposes of a heap, is that the tree can come into an array. And before we do that, I'll just explain sort of like a bit of a trivia game, heap or no heap, where I'll give you guys a little bit of time to decide if it's a heap or not a heap, given the heap rules. I'll write out the heap rules here in the greatest IDE of all time, and we'll see if we can identify heap versus not heap. So if I say heap rules. Alright, so the heap rules are 1. The root of each subtree must be the largest node in the tree. Or in, I guess, that subtree. In that subtree. 2. These tree nodes must be added left to right, top to bottom. So these are the rules of a heap. Right away, we're going to say that this visualizer, it draws binary search trees. It doesn't draw heaps. So we're going to pretend that this rule is always enforced. We're going to ignore the top rule for now. So for the trivia, we ignore this. We don't ignore it in real life. We don't ignore this one. So we just look at this. All right. We want to see if the nodes are being added left to right, top to bottom. So let's take a look. Is this a heap right now? Yeah. Yeah, it's a heap right now because all of the nodes have been added left to right, top to bottom. If I add a random one, is that a heap? Well, is it added left to right, top to bottom? So left to right on the top level? Yeah. Left to right on the second level? Yeah. Left to right on this level? No, because 12 has no children. It should have only a child on 12. So this is not a heap. Let's make it into a heap. To make this into a heap, I could remove the 102, but that would not be very productive to our understanding. So instead, I'm going to fill up that 12 one. So I need something smaller than 12. That's why I'm going to set this one's level to be like 2. And then I want one that's bigger than 12, but smaller than 73, so maybe like 26, right? Now this is a heap. This is a heap because it goes 78, 12, 190, and then these are all filled top to bottom, left to right. These are filled top to bottom, left to right. Why do we care about top to bottom, left to right? Well, imagine instead of a tree, we were to store this data structure in an array. Instead of having it in a binary tree with pointers, we do it comme ça. We've got our array, and I'll just turn this one into an array right now. So our array goes like this. It goes 73, 12, 190, 2, 20. Now, how do we know that we can make this array happen? How do we know that it's possible to have an array like this that encodes this binary tree? Well, it's actually pretty simple. It goes, let's call it head dot left, head dot right, head dot left dot right? So we can see how we follow through with recursively. And if we kind of do this in a way that's more thoughtful, maybe, we can say that for each element of the array, the index of its children is... Now, how do we figure this out? Let's look at the base case. For this one, we don't zero index. We're gonna not zero index this because it makes the math easier. What can we say about the index of the children if we flatten out our binary tree like this? Well, we can say that the index of the one to the left can just be the index times 2. And that's going to apply because every time we add a node to our tree, the number of nodes in the tree goes up by 2 to the number of nodes. Or I'd rather no, sorry, it takes 2 to the number of nodes, like number of depths that you want to have to get the next depth of the tree. And that property can help us a lot with these mathematical calculations. So if here we say, let's say index dot left is equal to 2 times index. Index dot right is equal to 2 times index plus 1. And then let's just say the opposite is true too. So index dot parent is equal to index over 2. So now what can we say? Well, why does this apply? Well, let's think about it like this. So we've got a tree here, and yes, I'm drawing it out in Vim for everyone. We've got a tree here where we've got a root, which we're just going to call, like, big. And then we've got children, we've got, like, small and small 2. And then here we've got tiny and tiny 2 and tiny 3 and tiny 4. That's our little tree. It's a beautiful tree, happy little tree. This tree is filled like this. So how do we know that our tree is going to have a index of its children when it's converted into an array? And in fact, I'll draw the array representation right now. So this one goes into an array, and it goes into an array. I'll just make this pretty really quick. It goes into an array like this, where we have it go big, small, small 2, tiny, tiny 2, tiny 3, tiny 4. When it goes into an array like this, what it does is it actually, it lets us get the children by indices. We have index 1 is big. We're not zero indexing, right? Index 2 is small. Index 3 is small 2. Index 4 is tiny. Index 5 is tiny 2. Index 6 is tiny 3. Index 7 is tiny 4. We've got these indices, right? Now we can test our math. We can say that the left child of big is small, right? So 1 times 2 is 2. That's correct, right? Left child of big is small. 1 times 2 is 2. Left child of small is going to be tiny. 2 times 2 is 4. How does that work out? Why does that work? Well, we're adding top to bottom, left to right. That's an important step. But also, we want to consider the property of a binary tree that for every next level, we need double the amount of nodes to make that level full, right? So we say level 1, level 2, level 3. I'll go for 3 levels because otherwise it's going to get really big. So at level 3, we're just going to have, well, I'll actually copy our tree. I'll copy our tree over, and can I copy it over? No, I can just copy every line of it over. So. Yeah, come on. Yeah, so there was 1 layer of the tree. We go back to insert mode. Then we have the next layer of the tree. And I'll copy these over just so I can show you guys, in fact, that every level, we double the amount of nodes. And that's why we can do this math. I'm doing a bit more explanation this time. If you want the super quick coding version, there's a Monday section where I just go into the code explanation of this, and I don't do the theory as much. Today I'm just going to go hard on the theory so I can differentiate the two sections a little bit. So here I'll paste that, and it's not pasting. I didn't copy it properly, probably. Come on. There we go. So now the number of things in each level, well, this one has 1 item, this one has 2 item, and this one has 4 item, and then we can not even fill them in. We can just say level 4 is going to have 8 item, level 5 is going to have 16 item, and then level, we're just going to call it level n is going to have 2 to the, I believe it's n minus 1. Minus 1 items in it. So why did I do this? Why did I spend all this time showing you guys how many items are in each level of a binary search tree, or any binary tree that's balanced? Well, here in the heap we know that when we multiply by 2, we actually get the same property followed. Like, okay, so big multiplied by 2 is it gets us to small, and then the same rules apply in that index. So big multiplied by 2 plus 1 gives us 3. It gives us then index 6 for the tiny, which is an even number here, and then the same rules just recursively apply through the subtrees. So here, when we're at 2 to the n minus 1 items in our level, right, when we're at that really, really low level of our tree, we still just recursively work at the same indices, and the math still applies because like it's just multiplying those bigger numbers in those subtrees within that range. So here, well, hopefully that makes a bit more sense to you, right? Like since we have a binary tree and we're multiplying the number of things by 2 at each point, the multiplication by 2 to get the children just kind of factors into getting that index there. And then it recursively applies down through the tree. I don't know if that was super concise, but hopefully it makes the theory a little bit more clear on these getting the children from the numbers. So now that we have an idea of getting the children from the numbers, and if you have any questions, please ask. I will be happy to answer. And I should probably pull up the chat before I forget. That would be wise of me. Yeah. Okay. Cool. So. Yeah, we've got the heap rules, we've got the arithmetic. So now we can start actually implementing our heap. So this is a heap because it goes top to bottom, left to right. Let's do it here. So in here, we want to start by filling in our index ones. We started by saying left index is 2 times the I, right? So left index will be 2 times I, and then we'll return that. I don't want to just do the multiplication for a reason. Right index will be return 2 times I plus 1. Has left child, we'll say, well, this is actually something we'll have to do when we have the number of items in our heap. So we'll come back to that, and parent index will be return I over 2. Private t parent will be, yeah, that's cool, just return. And we should probably create this array now. And then, but before I do that, I gotta create the heap. So what is the heap? Well, the heap is just this array. It's gonna be an array right up here at the declaration. And I should probably actually also declare all my other fields. So we're gonna say a private array of t called heap. We're gonna say a private static final int of default capacity, and we'll make it 10 for now, and we'll say a private int size, and we'll say a private boolean min. Now what are these for? Well, min, we'll say if this is active, we put the smallest item in the top priority spot. Size says this is how much crap we put in our heap. Default capacity says this is how big the array starts and how much it grows every time it needs to grow. And this is the array into which we smush our tree. So with these, hopefully it's more clear. I'm even going to copy paste my little explanations here. By copy paste my explanations here, I mean I'll actually copy paste my explanations here, put them into the just the top here, so we know exactly what we're doing, and get rid of these slashes. Cool. So that's our little explanation of some little details about the heap. And then there's our fields. So we can go back to our helper methods now. Has right child. How do we know if it has a right child? Well, we know how to get the right child. We get the right child by multiplying by 2 and adding 1, right? But how do we know that it's actually within our data structure? Well, we can say return right child, right index of I is greater than or equal to size. Or less than or equal to size, yes. And that's how we know if it has a right child. Exact same logic for the left child. We just say left index, and then there. Good to go. How do we know if it has a parent? Well, if it has a parent or not, it just depends on if the index is valid, right? So we can say return I is greater than 1. Easy peasy. So we've wrote our easiest methods now, and now a swap method. This is simply a swap method in an array. We've written these 100 times before. I don't even need to explain it. We just say index 1, make a temp, and then we can say, heap at index 1 is equal to heap at index 2. And if you want to get a refresher on this, there is the first few tutorials. I think tutorial 1 or tutorial 2 has this in it, and that is what I would recommend seeing. And then here we've swapped out these elements. This is going to be helpful for us because we're going to be calling swap a lot in bubble up and bubble down. So what are bubble up and bubble down? Well, remember when I said the heap has this one rule, and we didn't talk about it first, but we got to talk about it now. It's that the root of each subtree must be the largest node in that subtree. That is what bubble up and bubble down is for. So this is what bubble up and bubble down are for, aka up heap, down heap, etc. These methods will ensure that a given node is in the right spot and will move them accordingly. Now up and down refers to up and down on the tree. So up heap will take something from here and move it up if it needs to, and down heap will go down. That should be relatively clear, hopefully. So now we can see about writing those right about now. And I'll start with bubble up. I'm doing this backwards compared to last time, again, just so that there's some difference in the way the logic is explained. Bubble up, we're going to start at the end, right? Because the lowest down is our last index. We're going from the bottom here in bubble up. So we start from the bottom. So int index is equal to length. Or we can say size here, because I have it sized this time. Now, if it's a min heap, we behave differently than it's a max heap. So I'll create that min max right here. So this is the case of a min heap. This is the case of a max heap. Max heap. In fact, actually, we can make a common code base for some of our bubble methods. I can take most of this so far, and I can copy paste it to max heap. By most of it, I just mean, or by down heap. I can copy paste this part, and then I have to change index from size to be 1 in the other direction. But we can do that. And we'll paste those in there right now, so we don't have to duplicate the code. And here we'll say start from the top. Right, start from the bottom. Now we go in here. So now we're here, and now we want to do very simple logic here. This is like a elementary school level method. You've all done this kind of thing before. All we're doing is literally the same kind of thing as we do in bubble sort. We just say while it has a parent, and obviously I will be the current index, so index, and the parent of the index dot compare to, and since that's because we're using generics, heap at index, so compared to the actual thing at the index we're using, while that compared to that is indeed greater than 0, we will swap them. Swap it with its parent. Very easy, very fun. Index will be equal to parent index of index, and we'll go up the tree. So here we climb up the tree, swap with the one above, bubble up. Right, and now here we're saying if the parent exists and is bigger or smaller in the case of a max heap. And then I'll not even comment that, and then I'll say the case of a max heap, it's just like the min heap, but the is now a. Right, so it's actually like, it's quite literally identical. What I can do here for us is I can actually just copy paste it, and that will work just fine. But I'll have to copy paste it properly so it doesn't break. Bam. And now instead I'll put it like that, and I'll get rid of this comment for bigger, and I'll just say smaller. Right, easy peasy. This method is quite simple, and it's as we can see, it bubbles things up if they're in the wrong place. So I'll even write that in the Java doc. I'll be very clear with it. So this method starts from the bottom, then it starts from the last node added, then it checks it against all of its lineage, parents, dot parent dot parents, right, and makes sure it is in the right order. Now I'll give a little bit of a challenge here. What do we think the time complexity of a bubble up is? Is it O of n because it goes through every parent, or is it maybe O of, well, it's not O of 1 because it does a while loop. So what could it be? Well, remember, what is the height of our tree? The height of our tree is going to be, well, it's going to be determined by the height of the tree ratio with the number of items. So what is the ratio of the height of the tree to the number of items? Well, if n is the height, so here I'll label this a bit better. So height, number of items. Well, for height n, it'll be n over 2 to the n minus 1. Right, and what does that look like? Well, n over 2 to the n minus 1. That's very much alike to base 2 of n. So height for size n will just be log base 2 of n, right here. That's how we know what the height is. So indeed, since we're traversing through the entire height of the tree, so let's say since we go through the height of the tree, we go through log n items. Worst case, O of log n. Perfect. All right. So how a bubble down now? We kind of started filling it in earlier, except now we start from the top, and we do a min heap case and a max heap case. Well, syntax continues to be similar. We do a while loop, but now it's different. It's while it has a left child on this one, because remember, we're going down the tree now. We're going to try to find one that's smaller, one that doesn't follow the min heap rule. So we're going to say int smaller is equal to left index of the index. And we're going to check if this is true after. We're going to see if this is actually smaller. And if it is, we're going to act. If it's not, we're not going to act. Now we're going to say if has right child index and heap at left index of the index dot compare to the heap at the right index of the index is greater than 0. So if there is a right child and that right child is indeed bigger, then the smaller is the right child. So what am I doing here? I'm saying guess the smaller is the left child. Arbitrary. If the right child is bigger than the left, it is well, smaller. Or I guess if the right child is smaller than the left, it is smaller. Correct the guess. Now, if the heap at the index, now this is just the checking if the if the current item compared to the one that's smaller, so the smallest of its children, is greater than 0. That's just the min heap check, so checking if it's actually smaller. We're going to enforce the heap rule, and we're going to say swap index and smaller. In fact, I think smaller is a bad name. Let's rename it to something more useful. Let's call it smallest child. Refactor, rename. No, I just want to rename it in the code occurrences. Give me a second. Rename code occurrences, and we're going to call it smallest child. There. Right, so if the smallest child is indeed bigger, swap it with the smallest child. That should make a bit of sense, right? Now, else we break, because the rule is being followed. Now, we'll say idx equals smaller. And there we go. There is our wonderful method. And we can even probably consolidate this a little bit more by putting these onto a line, if you prefer that, or if you don't prefer that. It's a short one, so we could. Makes it look maybe a little bit less intimidating. Here we've got that, else break, okay, and then we move on to the next. Move on to subtree. Subtree. Right now, else, this is just the case for a max heap, so we don't actually have to change a lot. So I'm just going to copy paste most of this. And for the max heap version, the only difference is that these have to swap. Little triangle boys, just got to change their directions, and the max heap will be enforced as well. Bigger, and then we just put the bigger instead of the smaller. Right? Max heap, min heap, very, very similar data structures to each other. They're just, well, different directions of the triangle things. That's all they are. Should make some sense. That's bubble up and bubble down. We've done all the hard methods now, actually, so we're left with only the easy ones. I know it sounds weird. I said the easy ones, and we see a remove. Isn't that weird? Well, let's go through it. Resize. We just have to do an array list. This is just I'm going to use the Java built-in methods. You all know how to make an array list if you want to do it without the copy of method, but I'm not going to bother. I'm doing it the lazy way. Heap.length plus default capacity. There, I'm resizing the array. Now, length, return size, peak. Well, how do we peak? Well, all we have to say is return the thing at the 0 index of the array. So, or I guess the 1 index, because we're not 0 index anymore. So, return heap at 1. Just show what is at the top of the array. Now, remove is actually just pop from a linked list, so or from a stack. So I'm just gonna rename it to pop here, so that it makes a little bit more sense, because we have peek and pop, you know, or we can say pulled. It depends how you want to define it, but I'll say pop. So we can do that, but first I'll do is empty. So I'll just return size is equal to 0. Alright, and now we're going to pop, which was previously called remove, but I think pop is just an easier way to understand it. I'm going to do it relatively, I think, inefficiently, but oh well. We'll have to suffer from that. So from int I equals 0, I is less than heap.length, I++, classic C++ style for loop. If value dot, not value. That's actually the proper remove method. Oopsies. Forgot we were doing pop and not remove. What am I even thinking about? That's the real... sorry, I started writing the remove method because we did it as like a bonus thing last time. Completely forgot we weren't doing it now. Oopsies. So t output equals peak. Alright, so we just peek it to get the output. We swap the one in the index 1 with the one at the length. No, length. Keep that length. No, actually, we want to use length. Sorry. Sorry, I just confused myself there. Yeah, we want to swap this one with the last one, like the last populated item in the data set. So we get to a base case by swapping the item we are removing out from where it was, the start to the end of the structure, so we can nuke it easy. Then we have to bubble down the one we swapped over to maintain the heap property. So we say, well, first we're going to remove it. So heap length is equal to null. We just kill it off. So kill it off after moving it to a secluded location. Let the garbage collection take away the body. Right. Then we just say length minus minus, or size minus minus in our case. Right. And then we say bubble down. Now what's that going to do? Well, it's actually going to move the one we just swapped. So this is going to fix our problem. So clean up the mess, get rid of the evidence. This one will bubble the one we displaced to replace the victim. Back down to where it belongs. So essentially, yeah, we're taking out our target. I guess our returning our target. Don't know how we want to describe that. Maybe documenting our target. Then return output will say delivering the target. Right, so we document our target, we do what we need to do with it, then we send it down to the slums where nobody will notice that it was taken away by garbage collection, which I will. We send our target to the slums where we can take it out without any hassle and let garbage collection handle the rest. Right. Then we also we bring one from the slums up to the top to temporarily take the place of the one we eliminated, so that there is no gap up there where gaps are hard to fill. Right? Then here we this should probably not be commented. Here we say we take the what do we call them, double back down to the slums after everyone has forgotten about the elimination. Now we're going to say change the records to show that the one we eliminated was not there. No. There. That's the full gruesome procedure of removing the top dog from the thing. Here we are removing the top element from the heap. Right? Nice, nice, nice. Now here we're going to do add. Add is also very, very easy. First we check if we need to resize, so if this dot length size is greater than or equal to heap dot size plus 1. And this dot resize. Right, now I'm just going to say size plus plus. That's just going to iterate our size, so we take note that we added something, so our size must increase. Set the value of the last index of the heap to be our added one, not the last index of the array, but the last index of our heap, the size variable. Right, so now we're going to say heap at size is going to be equal to value. Now we're just going to say bubble up, and bubble up will put it in its place. Let the newly added member rise up to where they belong from the slums. Perfect. Now we just need the constructor, and the constructor is also pretty straightforward. So heap is going to be, since we're using generics, we have to do some weird casting stuff, but we won't have to worry about that, and I don't think any assignments we're doing in this course. So heap is going to cast to that, and it's going to be a new comparable with a default capacity size. Right, and then we're going to say, the size is going to be 0. This dot min is equal to min. And, for item or t item in array, we're just going to add those to here. So we're going to say add item. And then we're done. We just heapify the array we're given, and we can even create one that's empty as well. So if we want to have another constructor where we don't have to give it an array from the start, we can just say get rid of the t array, get rid of that, and then we've got our other constructor right here ready to go. And that should be every method covered of the heap, top to bottom, easy peasy. Now we can actually watch it run. I'll create a little main method here. Do we have one? No, we don't. I'll have to write one. Oh, it's okay. We will. Let me just make it a bit nicer here. And I'll write public static void main string args. And first thing I'm going to say is maybe what kind of heap do we want to have? What do we want to have in our heap? I think we should have integers, because those are easy. So int nums is equal to new int, and we're going to maybe make it size 25, no, 20, just because that's a fun size. Now we're going to say for I equals 0, I is less than maybe 19, I plus plus. We're going to say nums. Oh, we don't need to do 19. I can just say. Oh, it's not 19 because it's not equal to, but yeah. Nums.length. We're going to say nums I is equal to, and I'm just going to do a randomizer here. So rand is equal to new random. Rand.nextInt is what we'll be filling it with. So I'll do rand.nextInt, and it's going to have a bound of, let's say 100, so it's nice. Okay. Now I'm going to say, heap integer test subject is equal to new heap. And we want a min or a max heap. And I'm going to say true. I don't even remember which one that is. It's a min heap now. And now we're going to say for integer I in nums test subject dot add I. Nice. And then we can say for int I equals 0. Or actually, no, we can just say, yeah, we can say for int I equals 0, or we can say while exclamation mark test subject dot is empty. System.out.println test subject dot pop. So now this should give us our numbers in sorted order printed out. Let's just make sure it does. And it doesn't. Index 10 is out of bounds for index 10. Nice. Yeah. It's our add method. It's no bueno today. No bueno. Okay, let's fix that boy. What do we have here? Heap at size is equal to value. Size plus plus. That's why. I did a +1 instead of a -1. Forgot to resize it. Okay, so 6, 7, 8, 12, 14, 16, yeah. Okay. It looks like it's indeed printing them in order. So now if I make it from a min heap to a max heap, so max is going to be, or min is going to be false. Let's try that. Let's see if it's going to have different numbers now, but we'll go biggest to smallest now, right? So our pop is working. And I'm kind of curious to see how bubble up works. I think bubble up is pretty cool. So why don't we watch bubble up work just by using breakpoints. So I'll debug it. I'll put my breakpoint here. And then we'll use step over and step into to get to where we want to be. So our heap is now full. We've got, what's it called? It's called test subject. Or no, it's not full. We just got to add it. So, or we can just use the constructor here, actually. That would be smarter. Let's just say nums. We'll re-debug that. Ah, forgot the order of the... Did I? Ah, cool. I'm just going to make it an integer array. Classic reference types. Alright, re-debug that. I'm just going to see if... What is wrong with you? Oh. They put the brackets there. Silly. Okay, now we should be able to do it. Cool. So now we have our heap. It indeed has a size of 20. And its heap looks like that. It goes 16 out of order. Isn't that kind of weird? But if we think about it, this is supposed to be a tree, right? So let's actually draw out the tree representation and see what's going on. So, oh, it's already open. So here, I'll just go down a little bit. Okay, so remember that index times 2 is going to be our next child. So it's going to go 96. Then what's 96 times 2? That's going to be its left child. It's going to be 93. Oh, we can also just go, we don't have to follow the math rules. We could also just go, left down. So 79. 93. And this is not a binary search tree, remember. 70. 77. The only rule we're following is that every subtree must have, every subtree must have a parent larger than the children. No, your parents can't be younger than you, so that's the rule. We did 77. Now we have 52. 67. We do 69. Nice. We do 2. We do 47. We do 37. We do 31. We do 57. And I'll make these a little bit more clear, maybe. Just a little bit more lined up with the other ones, so that we can see exactly which node has which children. Cool, okay. Now we're just going to go through the last few ones. 57, now we go 36. 19. 67 has children of 24. 56. And the nice one has a child of 16. There. So that's actually our tree right now. So we've got our tree representation, and we've got our array representation just next to each other right here. These are the same thing. And now I can show you guys maybe the math for it. So if I want to go left, right, left, I can go index left, right, left will be left, right, left. It'll be nice. That's a very good number. That wasn't even intentional. And now, so what I did was left, right, left. So I go times 2, that's left, times 2 plus 1. So 2 times 2 plus 1 will be 5. And now left again, so 10. See, same traversal. So left, right, left again. Go times 2. Right is times 2 plus 1. So we go to 5, and then times 2. There. And left, right, left. Does that make sense to everybody? That's the traversal, left, right, left. Left, right, left. And that's the tree, and that's the array. And I'll even, that's so beautiful, I'll even screenshot it. And I'm just going to check my recording is actually running. Perfect. All right. So there it goes. We've got left, right, left, all working. Now, what else do we want to do? Well, yeah, we can watch bubble up and bubble down working in the debugger. Let's do that. We've just paused here. We don't need to. We can actually step into over here. We'll just step into this one. We want to step into test subject.pop. So t output is equal output.peak. Don't care. Swap, don't care. Well, actually swap we do care, because look, it's going to be not following the rule anymore. What's 16 doing up there at the top? 16 does not belong at the top. That's bad. We got to fix this terrible predicament. So we go through and we go into bubble down, and this is where the terrible predicament gets fixed. So right now our heap is 16, 93, blah, 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 blah. 16's at the top, right? So min is false. It's a max heap. So 16 shouldn't be at the top. We go through. We check the children, right? And next to a smaller child. Now 16's moved down. It's bubbled down. Now it's going to bubble down, but it's going to bubble down to the spot that corresponds to where its children are. So it's going to be at index, well, 4 here. No, 5. Yeah, so it's swapped to index 5, and we can just watch it bubble down here. Now index 5, it's gonna first compare it. We actually do this manually, right? Left index, we'll just multiply it by 2. So what's an index 10? Nice. That is bigger, right? And we want the, well, actually it's gonna be biggest child for this one. And then the right one is gonna be 2. So it's gonna go to the one that is nice. Yeah. And it's gonna swap with our nice value. And bam. Now we've got 16 over there, and our nice value is bubbled up. So now 16 is going to be compared to what? It's going to be compared to, well, has left child times 2, 20. So it's going to be compared to the last one in our heap, is it? No, that index doesn't even exist. So it's not even going to be compared. It's just going to leave the loop. And now it's bubbled down to a place where the rules are being followed. That is bubbled down, working its magic. We don't have to watch all that. We should watch bubble up now. And then I can show you guys some quick speed test or step definition writing, and then we'll be set to go. So now bubble up. Well, we don't care about this one. Tiny size. We want to do it when it's saucy, so somewhere like here. What are we adding right now? I don't know. But oh, we're bubbling up, so we're bubbling 30 up. Now let's do something spicy. 32, 73. That's spicy. We want to watch that bubble up. So we're gonna go in here. Min is false. We're gonna say while the parent exists, so the parent does exist because we're just going to divide by 2. So the parent is, we're at index 16 right now, so the parent is going to be at index 8. That's going to be 15. Right, so it's going to be compared to 15, and we're going to check if it's indeed smaller, if 15 is smaller, and we're going to swap it. So is 15 smaller? Yep, we swapped it. There it is, 73. Now we're going to compare that to its parent, which is going to be 46. Is 46 smaller? Yeah, it is. So what do? We swap it. Oh, oops, well, actually, I didn't even need to do the next breakpoint. But yeah, then you should get it, right? We swap it with its parents until it's in the right spot. Now, the one at 18 is 1, so it's actually right. So what happens when it is actually correct? It's in the right spot. It's 1. It's tiny. So it's gonna check if the parents exist and are bigger. It's gonna fail that check. It's just gonna be done. It's O of 1 there, very fast. And now we just keep adding shit. Don't care. Okay, we good. So worst case log n, and in fact the same logic applies to this. But also we know that the best case is actually O of 1, because worst case O of log n, best case is going to be O of 1. In its place, worst case will be right. These are all simple. These are all O of 1, obviously. What other methods do have a time complexity which we might be curious about? Pop, well, that's going to be, well, this is going to be O of log n, right? So, best case O of 1 inherited from best case of, what is it called, bubble down, times its own complexity of O of 1, worst case O of log n, inherited from worst case of bubble down times its own complexity of O of 1. Right. Same thing applies to add, except instead of bubble up or bubble down, it's going to be bubble up. Now the constructors we don't really care for. Resize is actually O of n. Don't like that, but oh well. And that's that. We've got our time complexity sort of listed out. Now let's try put those to the test, shall we? So first thing I'm going to do is I'm going to create a method which helps me make heaps. So I'm going to call it, private static heap integer build heap long size, and we're going to copy our binary tree method, except instead of a binary tree we'll do a heap. So we'll say heap integer b tree, call it heap is equal to new heap. Do we want a min or a max heap? Doesn't matter. I'll just say max. Or that's a min heap. No, I said a max heap, I'll stick to my word. Now I'll say heap.add. And in fact, we can do strings, because I already had the string randomizer built in there. But that's going to put it already in sort order. That's going to cause us an edge case, because we took it out from the unbalanced. So I'll take it from the balanced. Now we'll return heap, and we'll change it to string just because that's already got a randomizer. Now how do we write a test method? Well, we start by typing at benchmark. Name is going to be heap add, or I just say add because I can make the category heap. Category is going to be heap public static long add to heap long input. So now heap string h is equal to new heap, or actually I need to say equals to build heap input. Right, so we've got our heap. Now we can just say string to add is equal to why don't I just make it the same random string that we added before? It's not going to have an I defined, but that's okay. We'll just put, that number for I. And now we're just going to say long start time is equal to system nanotime. H dot add to add long end time is equal to system dot nanotime. Return start time or end time minus start time. This is how you do a speed tester method really quick. And now notice the only method I call, including constructors, is the one I am testing. Now I can just do another few methods. I can copy most of this, but I just want to rename it, so I'm going to call it pop from heap. Most of this is the same, except now I'm just going to say h dot pop. Now pop from heap is done. Now what else do we need to write? We can say remove. No, we just did that one. So yeah, we can just do the pop and the push. Oh, then there was also the yeah, what else is there? No, actually that's good. O of 1 through to O of log n, that's fine. Okay, well we can just do these two speed tests for now. We're running low on time anyways, so I'm gonna run that. And I'm just gonna clear out this mess. It's got all my tutorials in it. And we're gonna add and pop. And we're gonna crank our data set size, not our step time, our data set size. Does it increase a lot? Well, it increases, but remember, it's O of log n at worst, and O of 1 at best. So it's really not so bad. Like, it doesn't increase really fast. I mean, it's a lot worse than O of 1. We can watch it leave O of 1 in the dust if we want to. Where's O of 1? O of 1 versus pop. But it doesn't really leave it in dust that much. It's like pretty good. The only thing it does is bubble up or bubble down, which is not the best. But yeah, it's not even running away from it. It's basically running an O of 1. Did I do an edge case? I might have done an edge case. Anyways, it is, in the absolute worst case, all it has to do is traverse down the queue to bubble it. But, you know, it's very rare for it to actually have to do that. Most of the time, it's quite fast. Now, what else do we need? Well, add compared to it. So yeah, these are very, very, very fast. In fact, what we could do is we could add a standard of log n to compare them to, but they're going to probably beat it, because remember, it's just the worst, absolute worst case bounding. It's not actually their expected speed. So I'll add another one, and I'm going to call it a public static long log n long input. Ooh, I don't have my adjustment factor, but it's okay. I'll just do like return 600 times log math dot log of input. Now we're 600. Is that good? Yeah, I'll do 600 times input. And let's just make it a benchmark. This is not going to be the same. It's not going to be comparable to our other math methods because I didn't write them in the same way, but still. Alright, now let's try comparing the bad math method log n to this. So, reset. Yeah. And that's too small. Let's also just do 600 times. Well, yeah, and it's stepping once in a while because it's correcting it. So yeah, it's going about log n. It's very, very, very comparable to it. Because log n well, it barely increases as you get larger, right? And these spikes you can ignore. Spikes are like background tasks and stuff, not to do with this. Or the resizing. For add, it has to resize every once in a while. That's why it does that. But here, yeah, we can see that it's basically scaling with log n. Pretty well. Not great, but like pretty well. And these spikes are add. What are these spikes? They are add. In case you're simply watching the recording, I will note that spikes are add by typing it in Vim. The spikes are add. They are when it resizes the array. Right. Okay, cool. So, we've got that going. Easy peasy. Fun stuff. Now that should be good to go for you guys. Hopefully you enjoyed this tutorial where we go over implementing the heap, its various time complexities, all that fun stuff, and some on how to do speed tester methods. Thank you so much for showing up. Enjoy your day. And if you have any questions, you're welcome to answer them or ask them now, and I'm happy to answer.